Swayam Prabha. Digital India. Educated India.
In this session, I would like to focus my attention on the use of a pair of overlapping photographs in order to make 3D spatial coordinate measurements. So, first of all basic concepts of stereo vision will be discussed and how the same can be used for viewing a pair of overlapping photographs to obtain 3D model so that subsequent measurements can be made. Finally, a brief discussion regarding the use of aerial photographs for mapping of ground information will be done. Stereoscopy is the term given to a natural phenomena of a normal human being who is looking simultaneously at two photographs that have been taken of the same scene from two viewpoints, viewing one photograph with each eye so that he can see an image of the scene in 3 dimensions. Stereoscopy or binocular vision is the facility which makes stereoscopy possible. Normal two-eyed vision is required for realizing and measuring depth by stereoscopy. Two primary clues are involved in stereoscopic vision. The first clue is the double image phenomena. Consider a pencil is held 12 to 15 inches or 300 to 375 millimeters in front of the eyes and the gaze is fixed on a spot on a far wall. Now, there will be two images of the pencil. The left image is found by the right eye and the right image is found by the left eye. When the gaze is now concentrated on the pencil, the two images of an object on the wall will be formed. The right image is found by the right eye and the left image is found by the left eye. If while the eyes are gazing at the wall, the pencil is moved away from the eyes towards the wall, there would be a position of the pencil somewhere in front of the wall where the double image would disappear. In other words, even though the pencil and the wall were at different distances from the eyes, both the pencil and the object on the wall are being seen as single images. This is called the depth of clear single binocular vision and is very important in stereoscopy and stereoscopic measurements. The double image phenomena can be treated quantitatively to determine the amount of depth. The second clue involved in stereoscopy is the relative angles between the lines joining points in the scene and the two eyes when the points lie at different distances from the eyes. In the figure below, the angle between the lines directed from object point A to the eyes is phi A and from the point B is equal to phi B. The 2 points are imaged at slightly different positions on the sensitive portion of the retina of the eye called the fovea centralis. The brain intercepts the differences in these positions as a difference in the two angles, that is phi A minus phi B, subtended by the interpupillary distance E and forms a spatial construction of the scene. This gives the impression of a distance d between two object points. The angle phi A and phi B are called the parallactic angle for the 2 points. For average separation of the eyes and for distance in the distinct vision of about 10 inches or 25 centimeters, the limiting upper value of phi is about 16 degrees. The lower limiting value of phi ranges from 10 to 20 seconds of an arc and represents a distance of somewhere between 600 to 800 meters for average size eye separation. Stereoscopic vision is not possible at distances close than 10 inches unless the eyes are aided by lenses, because the normal eye can not accommodate focus any longer. The perception of depth by stereoscopic vision is not possible beyond about 2000 feet or about 700 meter, as the parallactic angle is too small beyond the distance. In order to be able to perceive depth beyond 2000 feet, the eye's separation must be increased, as with a range finder or a pair of binocular, or else a pair of photographs must be taken at widely separated camera stations, and each photograph must be represented by the eyes for viewing. This phenomena is called stereoscopy. Now, let us look at the concept of stereoscopic viewing. The figure below shows a diagrammatic representation of the viewing stereoscopically a pair of photographs taken from two viewpoints. Suppose two dots of similar size and shapes have been drawn on a sheet of paper about 2 inch or 50 millimeter apart. The sheet of paper is placed on a desk or table, and the viewer looks downwards from a height above the table between 12 to and 15 inches, that is 300 to 375 mm. If he can make the left eye concentrate on the left dot and the right eye on the right dot, then a single image of two dots at some abstract distance d 1 from the image is formed. The impression of the distance d 1 is gained because of the parallactic angle phi 1. Now, a second pair of dots slightly more than 2 inches or 50 millimeter apart are also drawn on the sheet of paper, the lines joining the two pairs of dots being parallel with one another. On viewing these two pairs stereoscopically, the viewer gains the impression that the second pair of dots forms an image at some abstract distance d 2 from the eye. The increase in distance is caused by a corresponding increase in the parallactic angles, which for the second pair of dots is phi 2. The impression of the distance d 2 minus d 1 is caused by a difference in the parallactic angle, that is phi 1 minus phi 2. If the difference in the separation of the two pairs of dots on the sheet of paper is too great, then the viewer will not be able to hold the single image of each dot simultaneously, but will see a double image of one set or the other. Now, this concept of stereoscopic viewing is now extended to viewing of a pair of overlapping vertical photographs. In the figure below, two vertical photographs of the terrain are taken from two exposure stations L and L dash to give an overlap of about 60%. The images of the top and bottom of a tower appear on both the photographs as shown. The image of the top of the tower has removed further across the focal plane between exposures than has the image of the bottom of the tower. The relief displacement of the top of the tower with respect to the bottom is exhibited by both photographs. Further, the two images of the top of the tower lie at the same distance from the flight line as defined by the line joining the principal points, and that the two images of the bottom of the tower lie at the same distance from the flight line. So, in this figure, the two photographs have been laid flat on the table with the lines O O dash and the line O O dash lined up with the two images of the top of the tower about 2 inches or 50 millimeters apart. If the viewer now fixes his left eye on the left photograph and the right eye on the right photograph, he gains an impression of the height of the tower H due to the differences in the parallactic angles phi t and phi b, where phi t is the parallactic angle of the top of the tower and phi b is the parallactic angle of the bottom of the tower. The parallactic angle of each point is a direct result of the parallax of the point. Greater the parallax, greater is the parallactic angle subtended by the optical axes of the two eyes. When viewing the area of overlap photographs stereoscopically as just described, the viewer shifts his gaze from point to point. When the topographic relief is changing, he therefore perceives a continuously varying parallactic angle. This variation allows the viewer to gain a continuous uninterrupted stereoscopic image of the terrain. If a high nearly vertical cliff appears in the overlap area, the viewer will have difficulty in retaining the stereoscopic impression of the top and the bottom simultaneously, because the greater difference in parallax will exceed his depth of clear single binocular vision. The viewer will then see a double image of the top or the bottom of the cliff. Viewing a pair of photographs stereoscopically is performed by optical devices known as stereoscopes, which allow the simultaneously viewing of a pair of photographs. So, let us look at what actually is stereoscopes. There are two basic types of stereoscopes for stereoscopic viewing of photographs, namely the lens stereoscope and the mirror stereoscope. Each has its advantages and disadvantages. The lens stereoscope consists of two simple magnifying lenses mounted with a separation equal to the average interpupillar distance of the human eyes, but provision to change this separation to suit the individual user. The lenses are mounted in a frame so that they are supported at a fixed distance above the table top. The lens stereoscope presents a magnified image to the viewer. If the height of the lenses above the tabletop equals the focal length, the magnification is then approximately 10" or 250 millimeters divided by the focal length. Most simple lens stereoscope magnify about 2 times. A glance at the figure below shows that the photographs overlap one another to a certain extent when oriented under the lens stereoscope. Thus, a portion of the overlap area is obscured from the view. One or the other photograph must then be rolled back in order to view the entire area stereoscopically, or else they must be flipped so that first one photograph overlaps the second in order to view, say the left half of the stereoscopic image, and then the second overlaps the first in order to view the right half. Now, let us look at the mirror stereoscope. The mirror stereoscope consists of a pair of reflecting prisms or mirrors M, M dash, and a pair of wing mirrors capital M, M dash, each of which is oriented at 45 degrees with the plane of the photograph. A pair of meniscus lenses are located above the prism M and M dash in order to provide comfortable viewing of the stereoscopic image. One of the advantage of mirror stereoscope is that the photographs are completely separated for viewing and the entire overlap area can be seen stereoscopically without having to flip the photographs. Without the aid of binoculars, however, the scale of the stereoscopic image is small compared with the scale as seen through the lens stereoscope. Due to its size, the mirror stereoscope is not so portable as is the pocket stereoscope and is used in the field is somewhat awkward. Having had a look at the stereoscopes, now let us look at the procedure of placing the photographs, a pair of overlapping photographs in 3D. Before the stereoscopic or three-dimensional impression of the terrain may be realized, the photographs must be properly oriented under the stereoscope. This orientation, known as baselining, is performed as below. 1. Make certain that the photographs are consecutively numbered and in the same flight line. First of all, locate the principal point of the photograph. This can be obtained by joining the opposite fiducial marks of each photograph. Wherever the lines intersect, it signifies the geometric center of the photograph. Since it is assumed that the photograph is a truly vertical photograph, so the photograph center represents the principal point of the photograph. Transfer the principal point of the first photograph onto the second photograph. This is known as the conjugate principal point. Similarly, transfer the principal point of the second photograph onto the first photograph. Now, join the lines between the principal point of the first photo and the conjugate principal point of the second photograph. This line represents the flight line between the first photograph and the second photograph. Extend this line up to the vertical edge on both the sides. Repeat this for the second photograph. Now, take a drawing sheet and draw a line to represent the flight line. Place and fix the first photograph on the drawing sheet in such a manner that the flight line on the photograph is coincident on the line on the drawing sheet. Now, place the second photograph in the similar manner. Put the mirror stereoscope over the drawing sheet, obtain the pair of the photographs and view through it. Adjust the positions of the second photograph till the 3D view of the overlap portion of the pair of photographs is seen. Fix the second photograph at this position. Now, both the photographs are in 3D mode and the measurements can be made. If the two photographs are picked up and interchanged, the left eye sees the right hand photo and the right eye sees the left hand photo. Thus, valleys look like ridges and hill appears as depressions. This is called as pseudoscopic viewing of a stereo pair and is advantageous in delineating drainage lines because they appear quite unnaturally as knife edge ridges. Having discussed the procedure of baselining to obtain stereoscopic vision, let us look at the factors which may affect stereoscopic viewing. If a pair of truly vertical photographs, overlapping photographs is taken from exactly the same flying height and the photographs have been baselined, then a person with a normal binocular vision should be able to see a clear stereoscopic image throughout the area of the overlap of the two photographs. If both photographs are tilted and are taken from different flying heights as shown in the figure, a plane containing the two camera exposure stations L1 and L2 and the object A will intersect the two photographs along the two line segments L1, L2. The plane containing the airbase capital L1, L2 and the point A is called an epipolar plane and the lines small L1 and L2 are called the epipolar lines. When viewing a pair of tilted photographs under the stereoscope, the two photographs must be continuously shifted and rotated in order to create the epipolar planes passing through the points under observation and to be aligned parallel with the observer's eye base. Apart from the photographic tilt, under practical conditions, several factors affecting the photography and the orientation will tend to make stereoscopic vision quite difficult if not impossible. These factors are unequal flying heights, misalignment of the flight line, misalignment of the stereoscope, great difference in parallax between adjacent images. Now, let us look at the effect of unequal flying heights. It causes a difference in scale between two overlapping photographs. Even when there is no tilt in either of the photographs and the flight line has been aligned properly, the difference in the scales of the photographs will cause the distance between one conjugate image and the flight line to differ from the distance between the corresponding image and the flight line. This difference is shown in the figure below, wherein we can see the impact of unequal flying height. The left hand photograph is at a smaller scale than the right hand photograph because of a greater flying height. If the flight line is taken as the x axis and the y coordinate of A is smaller than the y coordinate of A dash by an amount equal to capital delta Y. Similarly, y b is smaller than y dash b for an amount equal to delta y b. The discrepancy in delta y a or delta y b is termed the y parallax of the point. Notice that variation in scale causes no y parallax at point C, which is on the line of flight. In normal vision, the optical axis of two eyes lie in a plane containing the eye base. That is, a person with normal vision does not look upwards with the left eye and downwards with the right eye. The slightest departure of one or the other optical axis from this plane causes serious eye strains. To correct for the situation shown in previous figure, one photograph must be moved slightly in a direction normal to the flight line when viewing different areas of the overlap area, or else the stereoscope base must be rotated until it lies parallel with a line through conjugate images in different portions of the overlap area. Relative tilt between two photographs in any direction causes y parallax to exist in different positions of the areas of overlap. Thus, the flight line is not truly defined by a line joining the principal point, but is defined by a line joining the nadir points. In the figure below, a pair of photographs is aligned according to the principal points. When there is no tilt in the left photograph, but the right photograph is tilted in the direction of the observer, the true flight line is indicated by the two segments O1 N2 and O1 dash N2 dash. If the stereoscopic base were to be rotated parallel with these segments, the amount of the overall y parallax would be delta y f. Added to the y parallax caused by tilt displacement of points on the right hand photograph. Thus, tilted photographs will cause a certain amount of eye strain until the tilt is corrected for by shifting the photographs and rotating the stereoscope slightly from one point to another in the area of overlap. When the flight line on a photograph is not properly aligned with the flight line on the overlapping photographs, the effect can be seen in the figure below. Here, it is assumed that both photographs are vertical and at the same scale. The y coordinate of A is equal to the y coordinate of A dash, but y parallax exists in the amount delta y A. The greatest difference in seeing the stereoscopic image because of the misalignment of the flight line occurs along the flight line itself and away from the center of the right hand photograph. Misalignments can be checked if the principal points have been transferred to their conjugate points and the segments of the flight line have been drawn on the photograph. When the photographs are properly aligned, the two segments of the flight lines should appear as one line in the stereoscopic image. Misalignment of the stereoscope is similar to the stereoscopic base not being parallel with the flight line and has the same effect as the misalignment of the flight line. This alignment becomes an impediment to comfortable stereoscopic viewing only when the stereoscope and the photographs remain fixed during the entire viewing period. Generally, the viewer detects and corrects stereoscopic misalignment in the process of viewing. At this point, a pair of photographs has been baselined so that the photographic based observations can be made. In my next session, I would focus my attention to the measurement of photographic parallax and how it can be used for determining height and other elements. Thank you.